Don't close the door. Okay, let's get started. Today we're going to try and finish up off policy RL. To start, we have Project Loon here, which is one of Google X's products where they use deep RL on a weather balloon. And so they had deep RL things like deal with unpredictable weather patterns and so on while flying this balloon around. So pretty cool real world use case. Okay, so remember where we are. We finished policy again. We're almost done with dynamic programming. And so today's lecture, we're going to start with off policy RL, recapping it, thinking about what it takes to get it to work in practice, thinking a little bit more about convergence, and then some frontiers. Okay, so we wanted to make policy grid work for robots. Remember, we started by trying to say we're going to replace this term in the policy grid with a Q function. A Q function is the expected sum of rewards in the future when you start at some state S, take action A, and follow the policy pi, right? And so a Q function gives you this average sum of rewards in the future when you act with A, and tells you how good some A is at some state S. And so in doing so, it helps you lower variance, and we show that you can also be off policy. Right? And so just kind of recap what we're doing here. We started by doing attempt 0, which is doing a Monte Carlo estimate, right? Monte Carlo estimate said we're going to get a bunch of tuples of S, A future rewards, regress. Problem is that it is unbiased, but it's high variance, and it's on policy, right? So we didn't want to do attempt 0. We went from attempt 0 to attempt 1. Attempt 1 was to use recursion in the value function. So that's the Bellman update. But you essentially collect data, you solve this recursive update to give you the value function, and then you get a Q function through one step look ahead. Right? So we did value function to Q function to policy gate. And so remember here, the good part here is that it's lower variance, but it's still on policy, right? You're still requiring data from the latest policy. Sorry. Yeah. So you're requiring data from the latest policy. And so the challenge here is that it's on policy, but it's lower variance. Okay, from there, we went to the last attempt, the one which is off policy and low variance, right? And so we often call this TD learning or SAC or Q learning, all of them share the same properties, but basically we use recursion directly on the Q function. And the important thing here was that your first action and the action in the bootstrap don't have to come from the same policy, right? So the AT that's on the left-hand side can come from the data. And this thing comes from the policy you're trying to evaluate, right? And so the data, which let's say is coming from some policy pi beta, and the thing you're trying to evaluate pi don't have to be the same. Right? So pi beta can include all your past iterates, and pi is your latest thing that you're trying to evaluate, and those two don't need to be the same. It's very good. And so that's what lets you be off policy. Okay, so that is the Q-Bellman update, and that kind of resulted in an update for TD learning, which says, let's try and make the left and the right-hand side of this recursion equal. So let's try and say that QSA is going to be R plus Q next S prime next A prime, where A prime is sampled from the policy, right? So SAS prime come from the data, A prime is sampled from the policy. Okay, so that's what lets you be off policy. Now you can replace the Qs on both sides with neural nets or any function approximators and solve this with SGD. The other important thing to note here is that you're not passing gradients to the right-hand side, right? Because you don't want both sides of your equation to move. So you're not passing gradients to the right-hand side. You're only passing gradients to the left-hand side. That's why whenever you see this update, you'll often have it as phi hat or phi bar, right? And that's why it's denoted slightly differently. Okay, so the interesting thing about doing this thing where you don't pass the gradients to the right-hand side is that you're not actually solving a gradient descent equation. So you can think of this as you are solving an objective that keeps on changing, right? So like every time Q changes, the target changes, right? But you're not solving like in gradient descent, you have a single objective and you keep just minimizing it. But here you're not, you're solving a series of problems. And so this is what you'd often call a fixed point iteration problem, or um, not quite the same as gradient descent. And so it'll have different dynamics. And that's what makes off-policy RL sometimes unpredictable with large models and large data sets. Cool. Alrighty. So, given this Q function, right, that's what we did the policy. Yeah.
The off policy, or right now I'm using off policy data. Why can't we just plug like the bottom equation back in, try figuring out something, and make sure we use like all clean off policy data instead of
So plug it back into where, sorry?
um this equation back into like the cube.
So I guess we're saying that this has to hold at convert. So we're saying that this is, right now what we've done is we decompose the Q into R plus future R. And we said that this equation holds at convert. And so you can think of what off-policy RL is trying to do is trying to find the Q for which this condition. Okay. And so you can kind of think of the next objective as like you're trying to optimize something so that the left and the right hand side. You're just trying to, it's like a little different than gradient descent, but it's like still trying to make the left and the right hand side. Yep.
In this optimization process, you freeze the queue on the right and then tune the queue on the left, and then you unfreeze the one on the right and replace it with
So you're just like not passing gradients to the right, but you are like, it is every time that you, the phi updates, phi have also. If you just like stop gradients with it.
I see.
Not for every problem. So we'll talk about that in a second. You can prove it for some like restricted class of function approximators, but for the general case, it does not converge. Good question. Okay, so once we have our Q function, the next step is to like update our policy. We only care about policies, right? And so we talked about two updates. The first is the likelihood ratio update, which is basically the policy gradient update. So you're going to just take this objective, use the like multiply and divide by P, use the chain rule, right? And that gives you this grad log pi times Q, right? Increase the likelihood of good stuff with Q, and decrease the likelihood of bad stuff according to Q. The newer update that we discussed was this thing called the pathwise derivative or reparameterization. And the idea of reparameterization is if you can separate out the deterministic and stochastic parts, right? So let's say pi was a Gaussian, then you can say that like your action is mu theta plus epsilon times sigma theta, where epsilon is sampled from a unit Gaussian. So it does not depend on theta. Right? Then the nice part here is that you can like rewrite this expectation in terms of something that does not depend on theta. And so you can send the gradient all the way inside. Right? And so this essentially like the difference between these two is like this one uses the zeroth order gradient. So it's like trying to sample and just like upweight the good stuff, downweight the bad stuff. This one is trying to use the gradient of the Q function. So if it samples something here, it's going to use the gradient of the Q function to do a set, right? So this one uses grad Q with respect to A. This one just upweights good Q and downweights bad Q. So the benefit of the right-hand side is that it's lower variance, right? But if the Q is wrong, then it's biased, right? And so, and the left-hand side is higher variance, right? But it does, and the right-hand side doesn't work for all policy classes, only when you can separate out the deterministic and the stochastic parts. Okay, so that is the policy improvement update. And when you put all the pieces together, you have an algorithm that looks like collect some data, go learn the Q function in a process you'd call policy evaluation, right? So get a Q function. Then you take an update on pi, which is policy improvement, like one of these two updates to improve pi. That's policy improvement. Once you've done policy improvement, you have a better pi. You go collect some more data, put it in the whole pool of data that you've had so far, and repeat. And so the reason someone asked last time why it's off policy, because you keep on collecting data, right? So it's online, but off policy. Now there's a class of methods which are offline, which is saying that like actually you skip this data collection step. You say that like someone gives you data, right? So like sometimes let's say you're in a hospital, you just have like records of people making decisions, and that's your offline data. Or if you're in robotics, a human goes and collects a bunch of data, not online, right? And then this field called offline RL basically thinks about if I had someone else give me the data and then I ran this process, like would that work? And so the challenges there are basically your data doesn't have complete coverage. It doesn't cover everything. And so this process becomes divergent when you don't have complete coverage. And so the challenges of offline RL, which we'll try to cover, are what happens if you don't collect data? There's only offline updates to the critic and the actor and the critic and the actor. Yeah. But if you're interested, go look up offline RL. There's a nice tutorial from Sergey Levin, maybe like 5 years ago, which is good. Cool. Alrighty. So I thought one thing that would be interesting to know about is this algorithm called SARSA. So this is the algorithm we've discussed so far, right? Which is TD learning. Remember that the thing on the left is from AT, which is coming from your data. Thing on the right is AT plus 1, which is coming from your policy, right? So it's off policy. Um, the there's an algorithm called SARSA. SARSA stands for state, action, reward, next state, next action. Like, but what SARSA does is it just samples the next action also from the data, right? And so the difference between SARSA and TD learning is that if you want to be off policy, you want to use TD learning because TD learning is a bit of an overloaded word, but I'm going to call this top thing TD learning. You want to use this because you can sample this and this from different policies. Whereas in SARSA, you sample the left-hand side and the right-hand side from the data, right? So it's kind of saying like you sample AT plus 1 from the same behavior policy that collected the rest of your data. So it's still going to do dynamic programming, but it's on policy, right? And so a lot of the early results in RL were through SARSA, and then people switched to more TD learning, but not a lot of people in robotics use SARSA, but if you ever wanted to debug your RL algorithm, SARSA is a good tool because one of the challenges that happens is if AT plus 1 is pretty OOD for Q, as in if like the policy that collects the data and the policy you're trying to evaluate are very different, like you start having like function approximation effects because you're going to feed in some actions that is really low likelihood under a Q. Whereas in SARSA, that mismatch doesn't happen, right? Because the left and the right hand side come from the same thing. So it's a good way to debug your implementation. But like a lot of the early results in RL were on SARSA, right? So for like backgammon and some of those things. Cool. All right. So that's a recap. Any questions before we keep going?
So in TD, you update your policy after learning the Q function, and when you're learning the Q function, you're relying on your policy for the next action.
Yes.
So do you sometimes do like a cycle where you like retrain Q and then like get the new policy and then you use that to retrain the Q again? Or?
Yeah, you're always doing a cycle.
Okay.
Right. So you're like I guess in practice, like how many times you do the Q update versus the pi update is a hyperparameter, right? But in some ways, like you can only do like you can only do some number of updates on a particular pi before you have to update the Q, right? But like every time you collect data, you go and update your Q, you update your pi for a bit, and then go like maybe re-update your Q after you collect. It's all such. Cool. Alrighty. So this is still like very much a theoretical concept. There's like some instantiations, but this version of TD learning is now what you apply in practice. So we make some small but important changes to get it there. So let's kind of go through those changes. Okay, so what are the changes that we make, right? So the first change that we make is like the algorithm that we defined earlier is like very much a batch update. So you like collect a bunch of data, then you do a bunch of Q updates, and you do a bunch of pi updates, and you repeat. But often in many practical implementations, you're doing online updates, which means that every time, because you're off policy, I don't have to wait. Like in policy gradient, right? I cannot even construct a gradient unless I sample a whole batch of trajectories. Like there's no gradient that exists, right? Whereas in off policy learning, let's say I'm like sampling along a trajectory, I'm taking like these transitions. I can like do updates asynchronously, right? So if I have all of this data, each time I get an SA S prime R tuple, I can do the update from off policy RL. I can update my Q, I can update my pi, right? And so what a lot of modern implementations of off policy RL do is that they do it online. So you would typically do collect data in batch, learn a Q function, learn a policy, repeat. But when you're doing it online, you kind of like are doing it, you're doing one gradient update per sample, right? And so you're saying that like every time I get a sample, I'm going to update my Q, I'm going to update my pi. Right? And the argument here is that you get faster gradient throughput, and so your behavior can change even during a trajectory. And it empirically seems to perform reasonably well. But the whole point is that like every time I get a transition, I will update my critic, I'll update my policy. So the whole point here is that when you're doing it this way, you can run an asynchronous thread. You can have something that's constantly updating things too, but your changes are much more immediate. Right? But if you just did this naively, like what's the problem that happens? Like, so the way to think about this is like you're doing a trajectory. Let's say you took some transition S A S prime R, and you then do an update for Q. Let's say you did like QSA minus R plus QS prime A prime, right? You just did like an update with one tuple. Like, what's the challenge here? Like, why is this not good here?
We get
Sorry.
like when you sample act like A prime,
Uh-huh.
I like it like Q of S and they kind of get extrapolated. So
But that's maybe true even in the batch setting, right? So, but things along that line, right? So like, one issue is that you have really high variance because you're not doing things on a batch, right? So you're doing things on individual tuples. And so if I'm doing, it's like doing SGD with batch size 1. And so maybe you don't want to do SGD with batch size 1, but then you can say, let me accumulate like K tuples and then do an update on that batch. And so the first thing you can try doing is like accumulate things for a while and then do an update. But what's the challenge with that? Like, why is that not perfect? Yeah. Right. Right. The optimal behavior at the beginning could be different from the end. And so I think the broader issue is that it's non-IID, right? Like every time you're doing an update, it's non-IID, you're also thrashing, right? Like you're saying, I'm going to change the behavior here, I'm going to change the behavior here, I'm going to change the behavior here. Right? And so if there's one thing we know from like the rest of machine learning, it's like IID updates are good. Like the more IID you can make machine learning, the better it tends to do. And so the challenges here are that you have correlated updates. Like if you're taking a bunch of things in sequence, like those tuples are connected, right? So it's kind of like if I do a bunch of updates, I just go one way rather than doing the average update that I care about. And so it's kind of like you go this way, this way, this way. And secondly, it just gets super unstable. To keep moving your policy and your Q function all the time gets pretty unstable. And so I think the original paper was like in the early 2000s, but the paper that made this popular was called DQN. It's like what started DeepMind back in 2013 or 14. But the idea behind DQN is to say that like instead of doing online updates of things in your batch, you put things into a replay buffer, and a replay buffer is just like it's like a ring buffer, basically a ring buffer where you store all your data, and you store all your data. Every time you get a tuple, instead of doing an update on it directly, you store it into a buffer, and then you sample IID from that buffer. So it seems like super obvious now, but it wasn't then. But the whole point of the replay buffer is that you're like decorrelating your updates, right? So the way that the algorithm would work then is that you're like, let's say, sampling these tuples, you dump it into a buffer, right? And then all your previous trajectories also had dumped into that buffer. And whenever you're doing updates, you can still do updates online, but you're doing updates on batches that you sample IID from the buffer, right? So when I'm like doing updates along this trajectory, I will of course have these things into the buffer too, but I'm sampling IID. And so by sampling IID, you're decorrelating, like you're not doing updates that are correlated with the current trajectory. Okay, so the replay buffer is like a super big enabler of modern off policy RL methods. And usually they're implemented as ring buffers. So you like remove things that are like the least recently used. Right? But there's other ways of like doing memory management here. But you can kind of think of it as just like something that stores all your past experiences. And then you want to do updates by sampling IID from that replay buffer. But a lot of interesting research is basically trying to think about how to sample from that replay buffer, right? So let's say I had a bunch of stuff in my replay buffer. I wanted to sample to do TD learning updates, right? What should I sample? Of course, the most obvious one is just sample randomly. What else? What else can I do to sample? Is there something smarter?
Maybe you could try sampling ones that you learn the most from.
Yep. How do you know what you learned the most from?
I guess remember how much error
Yeah.
last time.
Yeah. So you're getting at this idea called prioritize experience replay. And what prioritize experience replay does, it says like, look at the Bellman error. So look at how inconsistent Q and R plus next Q are, right? And like prioritize the things where that error is large. And that tends to speed up learning a lot. So sample more for more recent trajectories. Yeah, definitely. So there's like a whole body of work around how to sample from the replay buffer. And it may seem like a detail, but it's not. So here's another example that I like to think about, which is imagine that you had like a tree, okay? This is like your transitions. And imagine that you started all the values of your Q function at random, okay? So really what's going to happen is that first of all, these values are going to become correct. Then these values are going to propagate to here, and these ones are going to become correct. And then these ones will propagate to here, and these one will become correct, right? So that's how dynamic programming works backwards. But if I sample everything like just IID, what's going to happen is when I sample things IID, imagine that I like sampled all my Q functions are random to start. Like imagine I sampled this tuple, right? I'm like propagating a bullshit value into a bullshit value. And so I'm like wasting an update, right? And so a lot of the efficiency in off policy RL comes from like structuring your updates in the right way. And so what you'd like, if you want to have the most efficient pass here, you would like first do sample at the end, then sample at the thing one before, then sample at the thing one before, right? And so you don't waste any updates propagating things that are not important. Okay?
That sometimes you'll do your updates, and since it came from different, like, I guess, suppose you like sample the bottom two,
Oops, sorry, I deleted that.
like the queue of the target queue
It's wrong.
is wrong.
Yeah.
So is that a problem? Like
That's a
you could
problem. Well, like it'll eventually correct. Like the whole point is that it'll eventually under like for instance in linear function approximation or in tabular, it'll eventually correct. But you're wasting updates propagating values that are not important.
And
Okay?
how often do you update the target queue?
That is like a hyperparameter. So like what we'll cover that next, but you'll update the target every so often. But one of the challenges, like one of the interesting lines of work here are that you prioritize by the target error. So you don't propagate targets that are like incorrect. The question is, how do you know which targets are incorrect, right? And so you can use uncertainty as a
The buffer, are we doing it from multiple, like, their face that is running the same time?
So in the real world, there's only one trajectory, right? But in simulation, often you'll dump all your parallel trajectories into the replay buffer. So any experience you have, just dump it in the replay.
Oh.
Cool. All right. So cool. Yeah. Here's another way to think about why sampling is important in the replay buffer. Is like imagine that you had an offline setting. So someone gave you a bunch of data, right? So you can think about like, let's say you had like you can think of like RL as like kind of like search in a graph. It's like propagating values in a graph. Okay. So imagine that the goal was here. And now what I want to do is I want to figure out the optimal strategy here, right? But like imagine this was like a much bigger graph. and I like really don't, and there's only, it's a sparse reward, so the value only sits at this where I've drawn the star. So if the value is only sitting at star, and I like keep sampling updates like over here and over here and over here, like that star is not going to propagate backwards, right? And so in order to actually propagate value, I have to pick this, and then I have to pick this, and then I have to pick this, and I have to pick this with some likelihood to propagate value backwards, right? And so in some ways, you can think of like sampling in the replay buffer as being analogous to like exploration. You're just exploring in this like non-parametric representation of the space. Like you have to sample the good stuff in order to propagate it back. Or not the good stuff, but the informative stuff. Okay, yes.
Did sampling uniformly ever work well in practice?
Yeah.
It just seems surprising to me that totally decorrelating updates trajectory can get it anywhere meaningful.
Yeah, it really depends on your reward function. So if your reward function is like super sparse, then it doesn't work as well. But if your reward function is relatively dense, you're still propagating signal. And if your batch size is big enough, then you will sample things with some likelihood. So usually the fix is like denser reward functions and bigger batch size. It's a little unsatisfying, but but that's usually the answer. But most implementations do actually sample uniformly. So not for good reason, I think, just simple. Okay, so now let's kind of address the other thing that that we were just talking about, which is this target network, right? So the fact that like the left and the right hand side of this equation have a phi and a phi hat, right? And so this phi hat is what you call a target network. And so typically in most implementations, you will have two networks. You'll have two separate networks. One is phi, one is phi hat. And phi hat you can kind of think of as like lagging behind phi, right? So if you like if you pass gradients to both sides, it becomes unstable. And even if you set, this is phi hat, sorry. If you set phi hat to phi every time, it's like you're still moving the target every single time, right? And so the solution is like simple, a little hacky, which is to do move phi hat to phi slowly, which is just to do an exponential moving average, right? Which is saying that like this is what you call Polyak averaging, but it's saying that if you had like your previous parameters phi and your new parameters phi hat, or sorry, your previous parameter phi hat, your new parameters phi, that came from this gradient update, only move phi hat to like some average between them, right? And so this is in parameter space, but you like kind of move phi hat to phi slowly. Right? So you can always think of the target is changing, but the target is changing slower than the thing is updating, right? So it's like keeping the optimization stable. It's definitely a hack, and people have been trying to remove it, and different things have been shown to remove this in some ways, but this is what most implementations use. Okay, so practical version of off-policy RL that is close to what people implement. You collect some data, you collect a single sample, you add it to your replay buffer, then you sample from your replay buffer IID, or according to one of those strategies. You do one gradient update on your critic. Then you do one gradient update on your actor, on your policy. You go sample data again, right? So often you'll either have like a separate process that's doing updates, or like every time you do a sample, you'll just do a quick update. There's like hyperparameters you choose, which is like how many updates you do. And this is often what you'd call your like update to data ratio. You have to see the word UTD, it just tells you how many actor and critic updates you do per data collection step. Cool.
Just the question about convergence.
Yes.
If you learn your Q function, and then you take your gradient step, and then when you learn your Q function, you use the target as you use the previous Q function as the target. Does that not work? Like, does that naive strategy not work?
That's the one that's like more that's the like if you didn't do the exponential moving average, like you did basically if you set phi hat to phi every single time, which is what you're saying, right? Like that's often super unstable, like the target keeps moving too much.
Even when the batch size.
Even when the batch size is large. Okay. So this is like there's a bunch of algorithms like TD3, SAC, all of them kind of implement some variant of this, plus minus some tricks, right? We'll talk about the tricks both in TD3 and SAC in a second, but they're like not that different than this picture. Right? If you look through the code, they basically do some version of this. The target update here is this like Polyak averaging step. And is it? Yeah.
Networks train better when they start from random initialization. So after collecting a bunch of data, do you ever just like randomly reinitialize the Q function and start?
Yeah. That's a great question. So, I mean, when you're starting to learn, you often start random. You typically will start random, but there's like a phenomenon called plasticity that shows up often. If like model keeps learning for long enough, it shows up in off-policy RL. If a model keeps learning for long enough, like it kind of stops being able to keep improving. And so it becomes plastic. And then often what you'll do is you'll keep your replay buffer around and you'll reinitialize the network parameters. And that tends to work well. But it's like at least we're gonna have a speaker in May, Claire, who studied this a bunch. So she'll talk about it. Cool. Okay, so this seems like a reasonable thing to do. But a question that can be asked is like, if we have this thing with an actor and a critic, it's double the you have an actor and your critic, you have a target network, and you have like double the hyperparameters, right? Or triple the hyperparameters. So can we take this actor critic update and then can we get rid of the actor? Like, is there a way for us to just train a critic and still get all the benefits, right? So is there a way for us to just like represent everything implicitly through the Q function? Okay, so what are ideas for us to get rid of this critic? I don't want to have a network which is the critic. Like, how do I get rid of the critic? Yeah.
Yes, if we have a discrete action space, you
Right.
could just like use Q directly as the actor.
That's
so, like,
right.
higher Q values are
That's right.
higher probability.
Yeah, you can just do argmax Q. Right? And so the idea behind this next line of work, which is basically what you'd call Q learning methods, right? More so than actor. The previous set of methods were called actor critic because you have a policy, which is the actor, and the Q function, that's the critic. And this line of work, which is more like Q learning, DQN, Q networks, is basically saying replace the actor with an implicit function on the Q. So like, for instance, a simple one is pi of A given S is max QSA with respect to A, right? So as long as you can compute max QSA with respect to A, you don't need to have an explicit actor. You have to change your Bellman update. Remember, the Bellman update used to be Q pi SA minus R plus gamma Q S prime A prime, where A prime was sampled from pi. Now pi is Q max, right? And so you will just replace this by like max with respect to A inside the Bellman update, right? So the Bellman update changes to have a max inside, and then the policy is just max of Q, or like arg max of Q, right? And so, yeah, you can kind of think of this as like a simpler way of doing things. As long as you can do the max of Q, you can represent the policy implicitly, and I just have to learn a Q function, right? So the process becomes like this. You collect some data, you add to the buffer, you learn a Q function, and then you update the target still. But when you're acting, you just act by taking the max of Q. So no actor, just Q. Cool. So why is this not what everyone does? Yeah.
Like if you ever be the one that's like the maximum Q?
Yeah. Yeah, exactly. Well, the difference is like the actor is like trained iteratively, whereas here I'm just going straight to the optimal. Right? But yes, in principle. Okay, so what's the difficulty in instantiating this in practice, right? So as you were saying, like if I have discrete action spaces, this is easy to do, right? But if it's continuous, then how do I do max A? And so what are some ideas to do max A continuously in a continuous space? Yeah.
Other values to make discrete or try to find the closest. Like you have a table, your max able to find the closest.
So you can discretize, right? Or you could do like someone's nearest neighbors or something, right? That's one idea. Makes sense? Yeah.
Okay, this is maybe a bit of a long shot, but what if you tried like differentiating your Q with respect to your action.
Yeah.
Just to
Yeah.
gradient.
No, makes sense. Do this. So like sample to get max A, you sample some action and then you follow the gradient to get to the max. Right? The challenge is that it's slow. What are other ideas here? The stupidest idea is just sample a bunch of Qs, right? Or sample a bunch of actions, just like blast it with sampling. Okay. What are other ideas here to be a little more clever? Yeah. Yeah, some optimizer, right? Like let's say this is a 0th order optimizer, this is a 1st order optimizer, but you're running test time optimization here, right? So the challenge with test time optimization is that it's slow. Yeah, but it's reasonable. Is there anything we can do structurally with the Q to make this maximization easier? What are some ideas? How do I structure a Q function so the maximization is easier? Any ideas? Okay, so sorry. There's this interesting idea called normalized advantage functions from like a few years ago. But basically what they try to do is they try to structure the Q function as a quadratic, right? So, and more generally as a convex function, right? But if you can structure the Q function as a quadratic in terms of action, so what they kind of do is they write QSA is equal to V of S plus like quadratic in terms of A, right? So the Q function is still non-linear in terms of S, or non-quadratic in terms of S, but it's quadratic in terms of A, right? And so if it's quadratic in terms of A, then like you have an analytical max. And you can generalize this to like the broader class of what you'd call input convex neural nets, like things where you're like, it's convex in terms of one of the inputs, right? And so when it's convex, you can find solutions with a convex solver. Quadratic is particularly easy, right? But the cool idea here is that if you can structure, like this is still expressive because your value function is non-linear. It's just that your action dependence is quadratic. So it's kind of like in control theory, you like use like control affine dynamics or something, right? So you like use the control, like it's affine in terms of A, but maybe not in terms of S, right? And so a little bit of structural simplification makes this work really well. Okay, so maybe the last bit on Q learning is that if I have phi of A given S equal to maximum, it's deterministic, right? And so it doesn't explore. But RL is all about exploring the world to find new things. So if this doesn't explore, then how do I make it explore? I have to like, if it's a stochastic policy, I'll add noise, I'll explore. But with the deterministic actor, like something that's argmax, like I will never explore, right? So how do I get this thing to explore? Add some noise, right? So the idea is to add extrinsic noise, and the choice of noise makes a big difference, right? So the most common one is called epsilon greedy. Right? Epsilon greedy means that with some probability epsilon, you're just going to sample a random action. Like continuous space will just like add some noise, right? But there's like more interesting ways of doing this. So one strategy in DDPG and a lot of commonly used RL algorithms is to use what you call an OU process. And the OU process is temporally correlated noise, right? So you can think of this as like Brownian motion. You can think of an OU process as the integral of Brownian motion, right? And so this is what governs an OU process, right? But the way it like reflects on exploration is like this one is choosing noise randomly, IID at every step. This one is choosing correlated noise. So it kind of looks more like right? So like explores further parts of the state space. And so OU processes are super commonly used. More recently, there's been a line of work on what you'll call pink noise, right? So pink noise is like some mix of like this is very local, so it's very sharp exploration. You're like dithering a lot. And the OU process is nice to get further away, but like you can see these things are sometimes over smoothed, these spots. And so pink noise allows you to interpolate between this like overly local and overly global exploration. And you can think of pink noise as something where like your spectrum falls with 1 over f in frequency domain, right? So it's a noise process where the spectrum falls with 1 over f. And so, but the way it manifests is more important. You can see that it like gets to far parts of the state space, but does like much more fine-grained exploration. And in terms of like why this matters, it just makes a huge difference in the end performance of your off-policy RL algorithm. If it doesn't explore, you're not going to like ever improve. Okay, there's this work in practice. This is an example from Google from like 7, 8 years ago. They had this thing called the arm farm, where they had like 14 robots that ran all the time. And so there are these 14 robots that were collecting data all the time. And they used the silly strategy of just like blasting the maximization of the Q function with samples because they're Google and they can throw TPUs at it. But it kind of learned to do a bunch of cool stuff just with like brute force of policy RL in the real world. There's also ways of doing this that are way more efficient for like precise tasks. And so there's an algorithm called DDPG, and you can think of DDPG as basically an instantiation of this algorithm. You can think of DDPG as an instantiation of this algorithm, but with OU noise while collecting the data and using like reparameterization to sample through the policy, right? And so that's how you can get a bunch of stuff to work on robots, right? So now you've gone from like several hours of training to like just minutes of training. Not minutes, still hours, but like hundreds of hours to 5s of hours. Okay. Let's take a couple of minutes and we'll come back and finish the rest of our policy.
Well, I have a question about the difference between something that's checking off policy and on policy.
Yeah.
What's the difference between those two?
So usually when you say something's off policy, you're able to use data beyond just your latest iterative policy.
Where?
And when something's on policy, it is like it's using only the latest batch of data that happened. So when something's on policy, it's typically online, or it's almost always online. But something that's off policy can be online or it could be offline. Right? So like, for instance, in the actor critic algorithm could use, let's go back to this thing, right? I think the important thing is when you collect data, do you throw away past iterates or do you keep past iterates? So if I'm on policy, I only use my latest batch of data. If I'm off policy, then I use all my data. Right?
And sometimes a problem because you get.
So it's less efficient, right?
Right, it's less efficient and you could still get like high or higher
That's right, yeah. Or like imagine that you can kind of think of this as like imagine in a previous iterate you kind of had some data that like reached an object. Like why would you waste that data, right? And so you want to use all your data fast.
Is there any reason something on policy like EPO?
It's more stable usually if the batch size is big enough. Because like it does policy gradient, it's doing gradient descent almost. And so it like tends to be a lot more stable than.
So if you increase the batch size of this algorithm
Yeah.
like ton.
Yeah.
And this is only the previous.
Right. Okay. Yes, it's very cool. I had this, if you guys are interested, I had this paper from a few years ago called Discore, which tries to like come up with optimal strategy, not optimal, better strategies to sample from the buffer based on like the error in the target. It's a cool paper. Take a look.
Like, and then sampling many batches without regarding like.
Yeah.
I'm curious why the difference is.
Because you're not doing dynamic programming. right? So here you're like you're bootstrapping. So you depend, when you say bootstrapping, you're like Q depends on next Q. And so that needs to drop. Okay, let's keep going. So the algorithms I've talked about so far are good. They're better than PPO, but they still take like 2 to 3 hours. Like we want to learn in 10 minutes, right? So what do we need to do to get these to match performance in 10 minutes and match asymptotic performance, like do well in the do well in absolute performance at the end, right? And so there's two issues we're going to try and deal with. The first is called overestimation bias, and the second is insufficient exploration. Right? So let's start with overestimation bias. So the idea of overestimation bias, let's start with like the non-actor critic version. We'll just start with the Q-learning version of the Bellman update, right? And so the Q-learning version of the Bellman update has essentially Q minus R plus max of the next Q, right? And now the important thing here is that you'd never have the, and remember, Q is the expected sum of rewards in the future. Q is an expectation. But you are estimating the Q. You never have the true Q, which means that like this estimator of Q is like a random variable, right? So imagine that like this was the true Q. Like what you have is a random variable, right? Sometimes it's up, sometimes it's down. It's good in expectation. It's unbiased in expectation. But it is like stochastic, right? The estimator is stochastic. Sometimes it's higher, sometimes it's lower. But the tricky thing is now you have this like estimator you have this random variable for Q that's stochastic, but you put it into a max, right? So imagine that you had like, this is the true value, but you put it into a max. And so you're going to have like an optimism bias because you're going to say like, sometimes you go higher, sometimes you go lower, but you're going to be biased towards things that are higher, right? And so if you have like a random variable inside a max, you tend to be optimistic, right? So the way you can see this in empiricism is that if you have like DDPG, you have the estimated values and the true values. The true values are in the dotted lines and the estimated values are in the solid lines, right? And you can see that you're way overestimating the values like across both things, right? And so in general, whenever you do off policy RL, you have this like optimism bias because your Q is a random variable and you're putting it inside a max. So let's try and understand this a little more clearly. Here's a figure I stole from Sergey. But basically what you want to do is you want to first compute the expectation and then take the max. You want to get the expected Q value, and then you want to take the action that gives you the max and the expectation. So you want to compute the max of expectation. But because your Q value is a random variable, you have the expectation of max. And expectation of max is higher than max of expectation, right? So here's an example. Imagine you had these 4 values, right? The expectation is the line over there, it's 1. The max is 4, right? And you have another set of random variables for a different action. The expectation is -1, the max is 6. So the expectation of max is 5, but the max of expectation is 1. So you can just derive this because max is convex, right? And so if max is convex, it's just Jensen's inequality. Jensen's inequality will say expectation of max is greater than max of expectation, right? And so the way that manifests in Q learning is because you don't have the perfect Q estimate. If you're stochastic, you will let's say you accidentally estimated some values as being higher, you will propagate that optimism. Right? And so you're like even if like in expectation you take many samples, it'll be the right thing. You will propagate any optimism. And so you can kind of think of this as just directly coming from Jensen's inequality, which says that for a convex function max here, like expectation max is greater than max expectation. Yeah.
Are we optimizing at any of the updates that we were earlier? Like most of them are, well, there, yes, but I think the ones we drive for like after grade, I give.
So
Those are all expectations on the rails.
yeah, that's a good question. So in actor critic, you still do maximization, you just do indirect maximization. Yes. Because you're doing Q under some pi, but then you're maximizing that, like in the actor step, you're choosing the pi which maximizes. And so in some ways you are still you're still biasing towards things that are optimistic because somewhere you're doing maximization with the step.
I guess would
It is shifted to the actor step.
would it show up with like the data collector then when we roll out the?
It shows up in the Q values being inflated. Right, so let's actually go to an example, and I'll show you what I mean. So imagine that you had this kind of setting. You had state A. You could go B. You could go left to B, or you could go right to terminal state. The reward is 0 to go to the right and 0 to go to the left. But from B, you have like 3 actions. Each of them lead to a different terminal with like the Q values are have expectation minus 0.1, but variance 1. Right? And so if I was able to like perfectly estimate the Q values, they would all be like, it would be -1, -0.1, -0.1, -0.1, which means that I should never go to the left because like the left is clearly worse than the right. Yeah. But because they're noisy, right, the expectations might look something like, or like my current Q values might look something like that. Right. And so then like action 2 from B, I think will give me 0.5. And so I'm going to propagate that optimistic value into A, right? And then I'm going to choose to go left. And so like the problem is that if you have optimism, the optimism propagates. And so something that is like not actually good is going to be like optimistically propagated backwards. And so in Q learning, it's like pretty direct how the optimism shows up. In actor critic, it like shows up through the actor step. Right? So you're doing like, you're maximizing Q with respect to the actor. So in some ways, you can kind of think of the like actor critic step as implicitly doing this thing, but just in another update. But it still has a bias towards optimism, right? Because you're still trying to maximize Q. Okay, so the idea here is that because your Q is a random variable, you're over optimistic, and so you'll choose left even though you should have gone right. Okay, so if that's our problem, how do we solve it? Right, like we want to avoid these over optimism mistakes. So what's the solution to over optimism? Yeah.
Can you subtract it, right? Some matter.
What value to subtract, I guess, right? Yeah, but it's kind of like that, right? So like the solution that's often used is to be pessimistic with respect to like many different estimates. Right? So the idea is that like imagine that you had n different measures of Q, right? So you had n different measures of Q. Let's say this was the expectation, and you had n different measures of Q, right? So what you will do is you will take the min over all of them. And so the idea here is that instead of being over optimistic with a single Q that might be wrong, you instead train n different estimates of Q. So you have n different critics. And then when you're doing the update, you do it on the min of those critics, right? So you want to avoid over optimism. Now, the risk here is that you might be overly pessimistic, but empirically this tends to work quite well. Yeah.
How do you build in the differentiation between your different Q estimates?
You're not differentiating them, you're just training them independently. And so just like in an ensemble of like in supervised learning, we often train an ensemble and they will like, especially on things where you don't have a lot of data, they tend to be like different just because of the different initialization, different learning dynamics. So it's kind of the same. You just train them with it. Okay, so the only change we really make is instead of training one critic, you train n critics. And then when you're bootstrapping, you construct your target as the min Q, right? So if you're doing like actor critic, you would do min Q. If you're doing like, what do you call it? Q learning, then you would do like the max under the like, you would construct the min Q over all the ensembles, and then you take the max action under that min. Yeah.
What we have before is map of one vector number two, or one sample number two, one optimistic, and now we're taking an example for n. It wouldn't be like really, really pessimistic, but it wouldn't matter because then of the maxes of the.
So you're going to take a max of the mins.
Okay.
So you're still going to say like you're gonna do this, and you're gonna like do the max of the mins. So you're saying because the idea is that if you're over optimistic, you're like it's going to keep propagating backwards, and here you're like trying to kill that over optimism. Yeah.
Why is optimism the issue that still like roughly follows the shape of the proof?
So like I guess roughly follows the shape is a bit of a question mark, right? But like in this example, right? Like you went left when you shouldn't have gone left. So like left was lava and right was great success. And so it's a little hard to like intuit in high dimensional continuous spaces, but it tends to like manifest in much worse performance. Yeah.
like exploration.
You are arming exploration.
So like, is there like a balance?
Yeah. So what sometimes people will do is like rather than doing the min, they'll like take k ensembles and then take some quantile of those. Yeah, good question. And so like the max is optimistic, which will explore. The min is pessimistic, which will not explore as much, and you take some quantile that helps.
Is there theoretically some point at which it's unbiased?
No. We've entered there's this paper TD3 that argues in some tabular case it's unbiased, but in general it's all biased at this point. It's all biased. Okay. Cool. So this idea is the thing that powers algorithms like TD3. And essentially you just train an ensemble of networks. You do the bootstrapping with the minimum of those, and that leads to a huge performance gain, right? So this is TD3, and this is like DDPG. Like the only difference between TD3 and DDPG is you have like K things and you do pessimism, right? And the same thing is between, if you look up DQN and double DQN, it's kind of the same idea. Again, you have like a huge gap in performance.
What if instead of like taking the max or the min, you just use one network to choose which one to update to?
Yeah.
And then use the other to actually.
That's exactly right. Yeah. So the thing that I did here is like the ensemble queue. The idea behind these double DQN and those kinds of methods is actually to decorrelate the thing that is choosing the max and the thing that is propagating the value. And so actually you invented the idea, which is saying that like go back to this equation, right? So right now I'm like the same network is choosing the action and it's the thing that is propagating the value. And so the way that double DQN works, it says that like you have two networks. And so like, let's call this Q1. And like, you're going to first choose AT plus 1 as like the argmax under Q2. And then you're going to stick in AT plus 1 into Q1. But the idea is you're like decorrelating the errors, right? So if you have two different networks, with low likelihood, they'll peak in the same place because they're independent.
Is this preferred or?
In general, like you can kind of think of like double DQN as decorrelating between two and ensemble as decorrelating between n. And so in most, at least robotics applications, you would use like the ensemble with n. And so the more ensembles you have, the better you did. But it's slower. Okay, cool. So that's in general, like you don't lose a lot from double DQN or double Q learning or ensembles, like it tends to help. And what some folks showed is that if you like
this work, we demonstrate a robot learn.
If you like use this kind of algorithm on a robot, you can learn to walk in around 20 minutes in the real world, starting from scratch. So there's a robot that's trying to learn with I think some version of like SAC with these tricks added, and you can like learn a walking gait in just 20 minutes in the real world, which is like orders of magnitude faster than you could do with PPO. Like the PPO gaits look better for sure, but in a simulator. But it's cool that you can learn to walk in just a few minutes on different terrains. And so if you wanted to ever do fine tuning in the real world, like this is the right algorithm to use, or like algorithms like this. Cool. All right, so that's the first issue, which is overestimation bias. The second issue is that often you have agents that don't explore enough, right? And so the same thing that we did in PPO is going to kind of be a problem here, which is that you have like agents that you want to explore like this, but they often just collapse to like exploring like one thing at a time, right? And so that leads to like either huge variance or performance that never goes up, right? And so in most off-policy RL algorithms, like the exploration is just coming from noise in the policy. Right? If there's just noise in the policy, there's no reason for it to actually explore enough. And so there's a new class of methods came out maybe like 10 years ago, called like maximum entropy RL methods and soft Q learning, soft actor critic. The idea behind all of them is basically to just take your normal discounted sum of rewards objective and just add entropy to it. That's it, right? So it's saying that you like maximize the sum of rewards plus entropy. So you're encouraging the policy to explicitly be exploratory, and the optimal solution to this and the optimal solution to this are not the same, right? So the idea is that like there's like a bunch of nice papers on this, but you can kind of show that solution to the maximum entropy RL problem is solving like a robust control problem, or it's like trying to find a solution that is like mini-max off. It's like this thing and this thing will give you different optima, and it has different optimization properties. But intuitively, you can just think of it as like adding an entropy bonus says that like rather than doing this, you like represent things like maximum entropy, right? So if you had like, let's say this was the reward and there was like an obstacle here, what maximum entropy RL would learn is not just one solution together, but like multiple solutions together. Right? And so maximum entropy would favor the multiple solution strategy rather than the one solution strategy. And so where RL wouldn't. Okay. So when you do maximum entropy, you can work out what happens for the policy gradient. Like maybe this is good homework for you guys, but just take this objective and work out the policy gradient with an extra minus alpha log pi term, and you'll get an expression that looks something like this. But we're talking about off policy RL. And so there's like these series of super complicated papers around maxent RL, but really what they boil down to is something very similar. It's basically just saying you do a critic update, but you just subtract minus alpha log pi, which is like entropy, right? And in the actor update, you again subtract minus alpha log pi. And so that just encourages things to be exploratory. The cool relationship here is that in normal off policy RL, you have your Q function, you have your value function, you have your policy. But in maximum entropy RL, you have a soft Q function, a soft value function, and a maximum entropy policy. And so you can kind of think of these as like doing the max on the left, and you can think of the right as doing the soft max. And so we'll have a lecture on controllers inference in like 2 weeks, and we'll cover this in detail. But like the intuition here is that as you set alpha to 0, the soft max becomes the max. And so you can think of the max as this, and the soft max as this. Right? So rather than collapsing all of the probability mass to the mode, it like spreads the probability mass out around like other things. Okay? And so you can kind of think of like this is saying that if alpha was 0, you just concentrate all your mass at the mode. But as alpha is not 0, it spreads it out to other things. Right? And so, yeah. So the idea behind maximum entropy RL is to add in an entropy term. It lets you go from the max to the soft max, and that lets you explore a lot better. What this kind of results in is an algorithm that's like really stable when you have lots of different tasks and lots of different hyperparameters. And so this is some examples of this for manipulation. This is some examples for locomotion, for Mojoko tasks. And it's still like not that far from the state of the art, which is cool. So all we did is we took TD3 from the last thing, and we just added entropy to it. That's it. So like the thing you'll implement in your homework is a version of SAC. You'll just do minimum over multiple Q functions, and you'll add entropy. And when you look at the difference in performance, you'll see that SAC is all the way here. You have TD3, then you have PPO. Right? So PPO will eventually go up. It's just like way, way, way outside this page. The caveat here is that it tends to work well on easier problems, but for harder problems, it like can be quite unstable and hard to like guarantee that SAC will work, while PPO will usually work. Okay. So before we wrap up on off policy RL, some tips. Make your replay buffers bigger. They tend to help with stability because the smaller your replay buffers are, the more your data is churning. If your data is churning a lot, your Q function jumps around a lot. So bigger replay buffers help. You typically will start with, like, if you're doing epsilon greedy exploration, you'd start with large epsilon. You want to explore a lot and then bring down the epsilon over time. It helps to use n-step returns. So far we've been doing like QSA minus R plus gamma QS prime A prime, right? Now, instead of R, if you do a sum of R over n steps, that's what you'd call n-step returns. And so it helps to have n-step returns because it propagates value directly over n steps. So it's kind of like action chunking from imitation learning. You want to propagate value directly. And sometimes in off-policy RL, it can be unstable. The gradients blow up. And so either clip the gradients of your value function or use the Huber loss rather than the mean squared error loss. And so the mean squared error loss is this one, and the Huber loss is this one. So it like falls off a little less sharply, right? And so those things kind of help with implementation. So cool. So that's off policy RL, right? So let's recap what we did. We started by saying we'll go from batch to online, and we'll introduce the idea of replay buffers. Yeah. Then we said, okay, replay buffers are great, but we need a target network. Target network is lagging behind the main network in your like right-hand side. Then we said, okay, this has a problem of overestimation bias, and you deal with it with an ensemble. Then you add entropy. And yeah, I think that's basically all that we covered, right? Actually, we somewhere before this, we did like, if you don't want an actor, then you do max Q. Yeah. Makes sense? Bunch of ideas, but they're not that far off from the basic idea of off-policy RL. They're just like little tricks. But if any of you want to get rid of these tricks and just have a simple algorithm, that'd be great. But that's how the state of the art is right now. Okay. I think the convergence is going to take us a little longer, so I'm going to end this 10 minutes early today, and we'll go over convergence in more detail on Monday. All right. Thank you.
Term makes it a little bit harder to learn like harder problems. What do you mean like?
Not the entropy term, just like actor critic is harder to learn for harder problems because